Welcome, Nocturnal Minds, aboard. Your learning journey starts now. So, picking up from our discussion on realism and relativism, a natural question arises: what exactly is it that makes science scientific? For centuries, philosophers have pointed to the method. It's not just about studying stars or genes, it's about how you study them. The classic idea was there's one true scientific method, a universal recipe for doing science, right? But as we'll see, that neat picture has gotten fuzzier over time. Now, many think of method not as a single thing, but as a whole toolbox of techniques, rules, and procedures, maybe even different toolboxes for different jobs or eras. Now, when we talk about methods, they aren't all operating at the same level. Think of it like building a house. At the ground level, you've got the basic skills: how to hammer a nail, how to mix cement, the proper way to use a specific tool. In science, this is about running an experiment correctly, using equipment properly, collecting raw data. Then, moving up a bit, you have design principles: deciding where to put the nails, how to lay the foundation, maybe using randomization or blinding in a clinical trial to avoid bias. That's more about planning the investigation. But the really high-level stuff, the stuff that gets philosophers arguing for decades, is about evaluating theories. How do we decide if theory A is better than theory B? What gives a theory its warrant, its right to be accepted? That's the domain we're mostly focusing on today: the methods of theory appraisal. Philosophers often split the process into two parts: discovery and justification. Discovery is the messy, creative part, the eureka moment, the flash of insight, the weird dream that leads to a breakthrough. Justification is the careful, logical part, the peer review, the statistical analysis, the arguments presented to convince others. For a long time, the thinking was, discovery is just psychology. It's unpredictable and irrational. Justification is the real science, governed by logic and method. But things have shifted. Many now argue that method isn't just for cleaning up after the discovery. It plays a role in sparking the discovery too. Maybe certain ways of thinking or questioning guide where ideas come from. So, the lines between these two contexts are getting blurrier. Alright, let's start with the simplest view: naive inductivism. This is the picture most people get when they think about science. It's beautifully straightforward. You observe things, lots of things, and then you generalize. If every swan you've ever seen is white, then all swans are white. Simple, right? The process is laid out. First, gather your facts through unbiased observation. Second, use induction to jump from those specific observations to a general rule or law. This view neatly explains both how we get theories and why we should accept them. The method itself provides the warrant. It sounds great, but as we know, simplicity often hides complexity. But hold on, this simple picture hits some serious roadblocks. First, can we really start with pure observation, free of any theory? Think about it. To even know what data is relevant to, say, gravity, you already need some understanding of physics, some theoretical framework. You don't just stumble upon data, you actively seek out data that tests a specific idea. Second, how do we get theories about things we can't see, like atoms? You can't just observe an atom and conclude it exists. You observe chemical reactions, Brownian motion, and then infer the existence of tiny unseen particles. Enumerative induction doesn't cut it here. And finally, the big one, Hume's problem. Why should we trust induction? Can we prove it works logically? No. Can we justify it by saying it worked before? That's circular. It's like saying induction is reliable because it's been reliable. We're stuck in a loop. These problems show naive induction is too simplistic. Okay, so naive induction is flawed. Enter the hypothetical deductive method, or HD. This is a step up. It keeps the deductive testing part, but changes the role of induction. Here, induction isn't used to get the theory, it's only used to support the theory after you have it. The process flips. First, you guess a hypothesis. This could be anything from a wild guess to a carefully reasoned proposal. Second, you deduce what observable consequences this hypothesis must have. Third, you go out and test those predictions. Fourth, if the prediction holds true, that provides inductive support for the original hypothesis. Notice, induction is only used for the final step of validation, not the initial leap of creation. This cleverly sidesteps the first two problems of naive induction. You can start with a theory, and you can test theories about unobservables by looking for their predicted effects. But HD isn't perfect either. Problem number 1 is the Du Heng Quine problem. Imagine you have a theory T, and you make a prediction P from it. To actually test P, you need more than just T. You need assumptions about the initial conditions, the accuracy of your measuring instruments, the stability of the environment, etc. Let's call these auxiliary hypotheses A. So, you're really testing T plus A. If the prediction fails, did T fail, or did A fail? Maybe the instrument was faulty, or the conditions weren't quite right. It's impossible to isolate the theory completely. This makes testing ambiguous and highlights the underdetermination issue. The data might not uniquely determine the theory. Problem 2 is predictive equivalence. Suppose theory X and theory Y make identical predictions for every possible experiment. According to HD, they should be equally supported by any evidence. But intuitively, we feel like a theory that's simpler, more elegant, or better explains other phenomena should be preferred, even if it makes the same predictions. Relying solely on prediction seems incomplete. Frustrated by the problems of induction and HD, Karl Popper took a radical turn. He said, "Forget induction. It's a myth. Science isn't about accumulating confirming evidence. It's about making bold guesses and trying to knock them down." His method is conjectures and refutations. You propose a powerful theory. Then you try everything you can to disprove it. Design experiments specifically designed to falsify it. Look for anomalies. If the theory survives these attempts, it gets corroborated. Corroboration isn't the same as confirmation. It means the theory has passed a tough test, making it more likely to be useful, especially if it's highly improbable to begin with. The more unlikely a theory is, the more impressive it is to survive a test. Crucially, Popper rejected induction entirely, both for generating theories and for supporting them. It's all about deduction and the attempt to falsify. Popper's idea was influential, but it also faced major pushback. One key critique, famously articulated by Wesley Salmon, is that Popper might be hiding induction. Think about it. If a theory survives many tests, you might choose to act on it in the future. But doesn't that rely on assuming the past success predicts future success? Isn't that an inductive leap? Popper tried to deny this, but critics argued his notion of corroboration implicitly carried inductive weight. Another powerful critique comes from history. Does science actually work like Popper describes? Look at the history of physics. Newtonian mechanics faced anomalies for centuries before being replaced by relativity. Einstein's theories also had lingering issues. Scientists often patch up theories, ignore inconvenient data, or resist abandoning well-established ideas, even when faced with contradictory evidence. While falsification is important, the picture of swift, decisive rejection seems too simplistic compared to the messy reality of scientific practice. These critiques, especially concerning the historical reality of science, led to a major shift in philosophy of science, starting in the 1960s. Philosophers began looking more closely at the history of science itself. Figures like Thomas Kuhn and Paul Feyerabend challenged the idea that there's one universal method. Kuhn introduced the concept of paradigms, suggesting that science operates within a framework of accepted theories and practices during normal science, and only shifts during revolutions when a paradigm is replaced. For Kuhn, the rules of method weren't fixed. They changed with a paradigm. Later, he suggested some values like accuracy or simplicity were relatively constant, guiding choices between theories, though they weren't rigid rules. Then came Feyerabend, the anarchist. In his book Against Method, he famously declared that any rule can be broken. He argued that the diversity of scientific practices shows there's no single method, and any attempt to impose one is dogmatic. Anything goes, at least in principle. While Feyerabend's stance was extreme, Imre Lakatos tried to find a middle ground. He borrowed from both Popper and Kuhn. Instead of paradigms, he talked about research programs. Each program has a core set of central theories and a belt of auxiliary hypotheses used to defend it or make predictions. Lakatos proposed that we can objectively compare programs based on whether they are progressive, generating novel, successful predictions, or degenerating, failing to predict new things or constantly needing ad hoc fixes. This offered a more structured way to evaluate theories than Kuhn's values, while acknowledging the dynamic nature of science. Ultimately, the historical turn led to a broad consensus: method isn't monolithic. There's a pluralism of methods. Different fields, different times, different situations might call for different approaches. Some even argue that this pluralism is the real face of induction, a complex network of reasoning strategies rather than a single algorithm. Okay, we've discussed various methods, but a deeper question emerges: how do we justify the methods themselves? This is meta-methodology. It's not just asking how we use a method, but why we should use that method in the first place. What gives a method its authority? Two big challenges loom here. First, the old ghost of Hume. Can we give a solid, non-circular reason for trusting induction, even in refined forms? Second, the threat of relativism. If methods are pluralistic and historical, as Kuhn and others suggested, how can we claim any method is objectively better? If everyone just follows their own norms, doesn't that mean anything goes, relativistically speaking? Finding a rational basis for our methods becomes crucial. How do we tackle this justification puzzle? One prominent approach is naturalism. Epistemological naturalism basically says philosophy should be like science, empirical and continuous with it. When faced with skepticism, naturalists say, Hume demands impossible standards. Justification is whatever successful science does. Maybe we can even justify induction using an inductive argument, avoiding the circularity trap. And against relativism, naturalists say, let's test the methods. Which methods actually lead to reliable knowledge and progress in science? Let's look at which methods are actually used by successful scientists. Those methods are the ones we should follow. This is called normative naturalism or reliabilism. If a method reliably leads to true beliefs or successful predictions, that's its warrant. It's a pragmatic, empirically grounded approach to justifying methodology. Now, let's shift gears slightly and bring in the social dimension. Science isn't just abstract logic. It happens in labs, universities funded by governments and corporations, and it impacts society profoundly. Francis Bacon, a key figure in early modern science, understood this. His famous slogan, "Knowledge is power," hints at the social stakes. He envisioned organized research institutes, like his fictional Salomon's House, recognizing that science needs social structure to produce practical knowledge. Importantly, Bacon still believed in an internal realm, the truth of scientific claims and the methods used to establish them, distinct from the external social context. Later thinkers like Marx took a stronger stance, seeing science and technology as integral parts of the economic base, driving historical development and serving specific functions, like maximizing profit in capitalist systems. Robert Merton, a sociologist, tried to capture the positive side of this social dimension. He identified a functional goal for science, extending certified knowledge. To achieve this, he proposed a set of institutional norms. Universalism judged scientists by their work, not their background. Communism, knowledge should be shared publicly, not hoarded. Disinterestedness, scientists should be objective-free from personal gain. Organized skepticism, ideas need to withstand critical scrutiny by peers before acceptance. These norms, Merton argued, promote the goal of reliable knowledge. Of course, critics pointed out that these norms aren't always followed perfectly, might vary across cultures or times, and perhaps science has multiple goals beyond just certified knowledge. But Merton highlighted a crucial aspiration within the scientific community. Moving further along the spectrum towards radical sociology, we encounter the strong program in the Sociology of Scientific Knowledge, or SSK. This approach, championed by David Bloor, takes a much stronger stance. It argues that all scientific beliefs, regardless of whether they're true or false, rational or irrational, can and should be explained purely by social causes, the context, the interests, the culture of the scientists involved. It rejects explanations based on internal factors like reason or method. The strong program is built on four key tenets: causality, impartiality, symmetry, and reflexivity. Impartiality means explaining everything. Symmetry demands that the same kind of social explanation applies to both true and false beliefs. Reflexivity means applying these principles to sociologists themselves. The aim is a complete causal account of scientific knowledge, leaving no room for autonomous rationality. But the strong program faces significant challenges. The biggest one is explaining success. Science has been remarkably successful in producing accurate theories and technologies. How can a purely social causal model account for this? It seems highly improbable that socio-political factors or personal interests would reliably guide scientists towards successful theories. Rational models involving methods seem far more plausible explanations for success. Furthermore, the strong program's treatment of norms like objectivity or reason as mere social constructs raises questions about the nature of reason itself. Does it reduce reason to something arbitrary? Relatedly, concepts like meaning finitism, influenced by Wittgenstein, suggest that meaning comes from community consensus. Applied to science, this implies that the meaning of scientific terms and the validity of methods depend entirely on what the scientific community accepts. This pushes the relativistic implications even further. These debates, particularly around the strong program and postmodernist interpretations of science studies, ignited what became known as the Science Wars. This was a period of intense conflict, often portrayed as scientists defending objective truth against sociologists and postmodernists who seemed to undermine it. Accusations flew on both sides. Scientists felt misrepresented and attacked, while critics accused scientists of ignoring social realities and maintaining ideological biases. Figures like Alan Sokal famously published a hoax paper in a cultural studies journal to highlight perceived absurdities. While the fiercest battles may have subsided, the underlying tensions remain. The challenge now is to move beyond the duili and find ways to integrate the valuable insights from both the traditional focus on method and rationality and the important contributions of the social studies of science. That's where the ongoing conversation lies.